Let's see if we can take the indefinite integral of sine to the fourth, or sine of x to the fourth, sine of x to the fourth dx. And like always, pause the video and see if you can work through it on your own. So if we had an odd exponent up here, whether it was a sine or a cosine, then the technique I would use, if this was sine to the third of x, I would separate one of the sine of x's out. So I would rewrite it as sine squared x times sine of x, and then I would convert this using the Pythagorean identity, and then when I distribute the sine of x, I'd be able to use u substitution, and we've done that in previous example videos, and you could have done this if it was cosine to the third of x as well, or to the fifth, or to the seventh, if you had an odd exponent. But here we have an even exponent, so what do we do? And so the technique we will use, and I guess you could call it a trick, the technique or trick to use is, once again, you want to just algebraically manipulate this so that you can use integration techniques that we are familiar with. And in this case, we would want to use the double angle identity. So the double angle identity tells us that sine squared of x is equal to 1/2 times 1 minus cosine of 2x. Cosine of 2x. So how can I apply this over here? Well, our original integral is just the same thing as, this is going to be the same thing as the integral of sine of x squared, all of that squared, dx. Now I can make this substitution. So this is the same thing as this, which is of course the same thing as this by the double angle identity. So I can rewrite it as the integral of 1/2 times 1 minus cosine of 2x, and then all of that squared dx. And what is that going to be equal to? That's going to be equal to, well, let's see, 1/2 squared is 1/4, so I can take that out. So we get 1/4 times the integral of, so I'm just going to square all of this business, 1 squared, which is 1, minus 2 cosine of 2x plus cosine squared of 2x dx. Now, fairly straightforward to take the indefinite integral, or to take the antiderivative of these two pieces, but what do I do here? Well, once again, I've got an even exponent. Let's apply the double angle identity for cosine. So we know that cosine squared of 2x is going to be equal to 1/2 times 1 plus cosine of double this angle, so cosine of 4x. So once again, just make the substitution. So this is going to be equal to, and actually, let me just write it this way, 1/4, and I'll switch, well, I'll just keep it in this color, 1/4 times 1 minus 2 cosine 2x plus 1/2, I'll just distribute the 1/2, plus 1/2 plus 1/2 cosine of 4x dx. Cosine of 4x dx. Let's see, I could take this, not that one, I could take this 1/2 and add it to this 1, and that's going to get me 3/2. So add those together, I'm going to get 3/2. And so let me rewrite this as, I'm in the home stretch really, so this is going to be equal to 1/4 times the integral of 3/2 minus 2 cosine of 2x. And then, let's see, the derivative of 4x is 4, so it'd be great if I had a 4 out here. So let me rewrite 1/2 as 4/8. I'm just multiplying and dividing by 4 is one way to think about it. So I could say plus 1/8 times 4 cosine of 4x. And I'm just doing this so that it's, well, in theory you could do u substitution, but we've had a lot of practice with this. We'll say, hey, I have function, I have its derivative, I can just integrate with respect to the 4x right over there. So I guess you could say it's the reverse chain rule, which is really what u substitution is all about. And now I'm ready to integrate. So this is going to be equal to, I think we deserve a little bit of a drum roll, 1/4 times 3/2 x. See, derivative of 2x is sitting right over here too, so this is going to be minus sine of 2x. We can verify that this is, let's see, derivative of this is going to be 2 cosine of 2x, yep, we have it right over there, plus 1/8 times, well, sine of 4x. Derivative of sine of 4x is going to be 4 cosine of 4x, which is exactly what we have there. And then home stretch, we just write the plus c, plus subconstant. This is an indefinite integral. And we're all done. This wasn't the simplest of problems, but it also wasn't too bad, and it's strangely satisfying to get it done.